This lesson is for Module 1, Unit 2 on rest and motion, which is kinematics. Moving things, what are the things that move around us? We have a perception of that. Lots of things move around us. Even the sun, which we think is stationary, is moving in an orbit in the Milky Way. A house that we think is stationary is moving with the earth. So, everything moves. How do we recognize what is moving, what is not? Is there any method of this study? Well, this study is called kinematics, where we only look at the body and talk about how it is moving without considering what is causing its movement. Motion is a variety of things. Things will be moving in different ways, but to talk about it, we can then say that we have to talk about the body first. Different types of bodies can be classified as rigid or non-rigid. A rigid body is one in which all the particles of the system stay together. For example, I have a block here. All the points here are going to stay in the same way, however much the time may pass. A fluid system will be non-rigid, and therefore, we will be restricting ourselves only to rigid bodies. What kind of motion this will have? We will have to take a consideration on that. For example, a body may move in a straight line. If I pull it along this white patch in front of you, this block is moving in a straight line. We are not talking about the pull I am putting on it, but only that it moves. This motion could be in one dimension, that means along a straight line. It could be in a plane as on the table, or it could be anywhere in the space. So, motion in one dimension, two dimension, or three dimensions. What is the other kind of motion that you can talk about? Supposing this is a rigid system here and you talk about a vibration. This is vibratory motion. About a particular point, this system is going back and forth. A rotation would be something like this. That means, about an axis passing through this rigid system, you have the body revolving around it. You have motion in a circular track or on curved path that we experience every day. In this particular lesson, we are going to restrict ourselves. Why do we have to restrict when we have to talk about so many types of motion? Because in your course, in your class 11 course, you are going to study each of these separately. Motion in a straight line, motion in a plane, motion as vibrations, and you would also be studying rotation. You will do the basics of each of these. The reason is that all the motions that you see around you in real life are complex. They are made up of one or more kinds of motions. So, if you understand each one clearly, it will be easier for you to relate to different types of motions. So, we have so far talked about a rigid body, and let us again understand that we are only restricting our study with rigid bodies and in a straight line, moving in a straight line. Limited ourselves to this one, we have another very interesting thing to do, and that is that if the body is rigid, then I can take it as a point object. You can see a bus on the road and imagine a red dot on that bus. As the bus is moving, so is the red dot. Now, if you consider the bus to be a rigid system, this red dot is capable of telling us how it is moving, what direction it is going in, how it is changing its place from one point to another can be talked of in terms of the red dot movement. So, it is okay to say that a rigid body can be treated as a point object. So, it is in this context that we talk about point objects in kinematics. Let us now go ahead with our study and say that, okay, how do we know that a body is moving? How do we know that the body is at rest? That means we have to talk about the surrounding. What is the meaning of that? That supposing you look at the film clip, there is traffic in the film clip. The cars are moving very fast, some are moving slow. But how do we have this impression? We get the impression because we are seeing certain things which are not moving at all. So, in relation to that, in relation to the surrounding, these objects are moving, and that is why we say it is in motion. So, we need to describe two words, rest and motion, with respect to the surrounding. The meaning of the word with respect to means that around it you should have certain things which will give you the sensation that the object has changed its place. So, now that we have been talking about a rigid object, we have been talking about it moving in a straight line, we have been talking about surrounding, and we are now going to explain or think about rest and motion. We say an object is at rest if it does not change its position with respect to its surrounding as the time elapses. So, three things are there: the object, which is a rigid object, the surrounding, which is what is around it, and the time elapsed. So, all these considerations together will give us a sensation of whether the object is moving or not. So, let us take an example. Supposing I treat this as a road and I put some cars on it. These cars can move in a particular direction. They can be seen over here in front of you, and I need somebody to look at it. So, I have a person who is standing here and watching. Now, watch, this car is coming towards him, this car is moving away from him. In both the cases, he will get the sensation of motion in terms of what is around it. Supposing there is a building here, he will get the understanding that it is moving with respect to the surrounding. So, the observation is very, very important. So, with respect to the surrounding, the observer sees that something is moving or not. Take a look at this picture. In the picture, you have an auto in which some children are going, and you have two persons, maybe a father and a child, trying to cross the road, and there is a policeman standing there. So, there are three observers: the policeman, the man and the child. And if you look at it carefully, for the policeman, the auto is on his left hand side, and for the man and the child, the auto is on the right side. So, with respect to the surrounding, the observation is different, but it is the same auto. The point I am trying to make over here is that when you talk about something moving, with respect to the surrounding, the intention of the observer is also to be considered. Where is this observer located? How is he seeing this thing which is moving around him? So, if you are talking about this auto, this impression will tell you that the two different observers are seeing the same moving object differently. What about the people who are sitting in the auto? Do you think they'll feel that they are moving with respect to each other? When you are going in a car, your driver is driving you and you are sitting at the back, let us say. What happens? There is no change in the position of the driver with respect to you. So, you say the driver is at rest. But this entire system of the car, the driver and you and everything else in the car is moving with respect to the surrounding. So, for an observer who is standing on the side of the road, is going to see this entire assembly go past it. Everybody is changing their position in time, and therefore they are all moving. Should there be a red light, the entire system stops. Supposing there is now an observer on the side, he will say, oh, they are at rest. How does he come to that conclusion? Because the car system is not changing its position with respect to the surrounding. So, clearly you have to understand here what is the meaning of rest and what is the meaning of motion. So, rest and motion, and the three things that are key here: the object, the observer and the surrounding. In physics, we don't talk about surrounding and things like that just in any which way we want, because we have to make certain calculations, we have to represent this motion, we should be able to talk about it, we should be able to say, okay, this has moved from this point to another point in so much time, or it has not moved all for a very long duration, so it's been on rest for this duration of time. In order to make ourselves capable of doing that, what we do is to describe the position of the object in a better way. So, what we do is we consider a Cartesian system, the x-axis represented by the red, the green blocks here represent the y, and this is the z-axis. So, when I talk about this particular car with respect to this origin that is here, I will have to talk about how much of x and how much of z. So, in a plane you need x and y to talk where it is. Supposing you were talking about it moving in a straight line, then what would it be? I would be saying, okay, this car is moving in this direction, and say this is an extension of my x, then you can see here that the x value is changing. There is no change in the y and the z direction, because it has moved along a straight line. It is possible for you to imagine an insect going along the y direction, or somebody moving along the z direction. So, in one dimension, x, y or z are capable of talking about where this object is located. So, we use the Cartesian system, and followed by that a number line something like this, where you can imagine a 0 at any point, and you can say, okay, the object is located here, it has moved towards the 0, it has moved away from the 0. So, your capability or your ability to talk about where this body is at an instant of time improves, and that is why you do this. Now, supposing I talk about the same cars again. We have been looking at rest and motion, and that also for rigid bodies only. Rigid body because we can represent it by a point object. In our concern, the point object means that the whole representation of the rigid body can be done by just a point. So, we do not need to worry about the environment of this particular object other than what it is outside the object. So, in our review, what we have been doing so far, we have said that we have a rigid body and it is moving with respect to its surrounding. That means, it is not remaining in the same position with the time elapsed, and therefore, we say it is in motion. So, we describe rest as if a body continues to be in its condition of rest with respect to its surrounding, then we say it is not moving at all. But if it changes its position with respect to the surrounding, we say it is in motion. Now, we have also seen that this motion is relative. In our picture with the auto and the policeman and the man and the child crossing the road, we saw that different people saw the same motion differently. Let us take another example here. These are these two cars, and we have another car on which there is this man standing. If this car moves ahead and this man is stationary, then for him this car is stationary, not moving, but this one is. What will happen if this particular man is also moving in his car and so is this one? If the distance between them remains the same, he could say that it is stationary, like the example of the person who was sitting in the car and the driver and him had no relative motion between them. So, the person sitting in the car thought that the driver is stationary, and obviously this driver must think that the people in the car are stationary. But for an observer who is standing outside this car is going to feel and understand that the system is moving. So, we must be able to describe this in a better way, and physics demands that. And did you know that your brain is getting two different sets of information about your body's motion when you are moving in a car or a bus? Sometimes you must have heard of that people get sick in the car or bus. Why is this happening? Because the brain is not connecting the motion of the bus as it goes around on the highway. This is more pronounced when he is going on a hilly road. People may be looking outside at the scenery while the car is going all along the winding roads. So, the information from the eyes and the information from the brain are not matching. This becomes very difficult for some people, and this causes them to feel car sick. So, what they should do is basically they should look at a point far away at a distance and focus on that and not the road, so that this relative motion does not cause them to feel sick. So, now we are going to use some scientific vocabulary to talk about our Cartesian reference frame, which we had said earlier. What would this mean? That supposing this is my Cartesian frame of reference and I have an object which is moving. Let's do with just one car here. If it is stationary and our observer is in this and is also stationary, this is moving. If this particular object is stationary, for him it is stationary. The other option is that along with this frame of reference, this steadily moves along also. In this situation, he might feel that the car is coming closer to him. This sensation you might have experienced if you are going in a car or in a bus or in a train. What is the scenery outside? It seems that the scenery is rushing away. This feeling is coming on account of perception, account of the observer moving, and the observer feels that he is not moving, and everything on the side is the trees, the roadside houses, buildings, they will never move. But it is because of this perception in the brain that the observer feels that everything is passing by and rushing and is in tremendous motion. But that is not the case. There is another situation that may happen to this frame of reference. Here is the person, and supposing he is in the swing, like the swing in the park. So, he goes like this, like that and like this. This particular frame of reference is not stationary, nor is it moving with a constant way. It is just changing. This to and fro motion is going to cause the observer on the swing to see things very differently. Watch what it will look like for the car. The frame has come towards the car, has moved away from the car and coming again. This is not all. This particular frame could also be moving in a circle. It is possible that it is rotating about a particular axis, much like the way it happens in a merry-go-round in a park. So, you could be doing this with your frame of reference and such like. So, observer can be in any condition. So, then our work of study becomes very difficult. What is it that we should assume now and limit ourselves so that we study only the motion of the object in the simplest possible way? So, we describe inertial frame of reference and non-inertial frame of reference. An inertial frame of reference is going to be stationary. So, everything that is moving is with respect to this stationary point. The observer is sitting on this inertial frame and is also stationary. Or at best, this inertial frame steadily moves in a particular direction with the observer over there. And a non-inertial frame of reference would be that it is going fast or slow in the same direction, or it is swinging, or it is tending to rotate, any of those possibilities. So, we cut out all the possibilities of the observer being in a non-inertial frame. So, we have now limited our study to a rigid object which can be represented by a point. We have restricted ourselves to move along a straight line. So, it is motion in one dimension only. Then we have said our surrounding is fixed, or we are working only in an inertial frame, and that also a stationary one. Now, the point comes in that supposing I have to describe this motion, this change in its position, I should also account for the time. Why? Because then only I will say, okay, from time this much, this has moved, or this has changed its place, or it is not the same with respect to this frame of reference, and therefore, I can say, okay, at time instant 0, this is where it is, and at time instant say 5 seconds later, it is somewhere here, and say another 5 seconds later, it is somewhere here. So, I need to account for the time as well. So, having understood the non-inertial frame and the inertial frame, and that we are choosing only the inertial frame for our study, we have now got our limitations and assumptions in place. Let us therefore remove this frame of reference with the 3 coordinates, where we had the choice that the object could move along x, along y, along z direction. Let us remove this from our preview and consider motion only in one direction, say along the x. So, this is an extension of our frame of reference, and our object is now allowed to move only along the x direction. Whether it moves this way or it moves along this is one choice, or it is able to move along the y, in which case it would be like this, and as I said earlier that it could be an insect that is going up or down. You could have a choice of the z direction also. There is yet another possibility. Supposing I can make this turn a bit, but leave it stationary, I could talk about a situation where there is an inclination like this, and this would also then be motion in one dimension. Remember, this movement is along the x, because for the y axis now I have it also inclined with the same angle as here. This is what it is. So, this could also be treated as motion in one dimension, but you have to be careful, because if you are considering it like this, then in that case this inclination is not going to be correct, because this would mean that for describing every position somewhere over here, you will need not only the x coordinate, but also the y. So, this would be motion in a plane, but if you turn your reference frame to be like this, then this motion can be regarded as motion in one dimension. I will do this again for you to understand a little better. If the motion is along this, it is one dimension. If the motion is along this vertical, it is one dimension. If the motion is along this, it is again one dimension. Along this line, along this plane which is inclined to the horizontal in front of you, it could be taken as motion in one dimension provided a frame is fixed like this. Watch, this is y, this is z and this is x. This is a possibility, and sometimes while doing problems you can consider the motion along the plane as motion in one dimension provided you consider this angle and you know that these are the vertical. Now, let us limit it to just one dimension, and that also for simplicity let us take it x. Right here I have these blue blocks which are equal sized. So, let us say they represent 1 meter each. So, if I move from here to this point, I will take some time. So, there will be some time elapsed, and this new position that I have is going to be represented in a special way. Supposing I go a little ahead, that means this particular position will have to be distinguished from the one which it had earlier. Now, to make it simple, I am going to use this car. It is placed here. As you can see, 3 blocks, center of the car, I am treating it as a point object. So, consider again the center of the car and let us move 1, 2, 3, 4 again. So, from the beginning this is some 7 places away to this point. Now, this position and the one which was earlier has to be distinguished. How does the scientific notation do that? You can say, okay, so many centimeters, so many meters from a particular location which is your reference point. But scientific notation for it is given as xt. That means you write x and in brackets you put t. What does that mean? It means the position at instant t. Now, instant t is different from time elapsed. Time elapsed would be starting at this point and reaching this one, means so much time has gone into it. But the position of this point is given as x at this instant of time. So, I hope you can make out the difference between time elapsed and time at an instant. That means, if I word it in terms of numbers, it would be time at instant 0 when you start looking at whether the body is moving or not, and time at instant 5 which is 5 seconds later, let us say, and the position that you have at instant 5, that will be the position after 5 seconds. So, the time interval is 5 minus 0 and the position is x5. If I want to take it any further from this location, from the starting point, then this will be a new x value and I will have to talk about at what time. So, supposing the body is moving steadily like this, that means covering equal distances in equal intervals of time, then the xt variation will give me some kind of formal relationship. But if I take it like this, then the car stops, then it goes like this and then it stops and then say it goes very fast, I can have a situation like that also. It is in relevance to that that this xt becomes very, very important. How do we write it? I have over here a simple way to show you how to express it. You write x, you put the bracket and you put the time instant in between. So, 0 does not mean beginning of time, it means beginning of time when you start looking at the body, when you start saying okay, it is now moving, that is what is instant 0. So, right now if this is instant 0, then I can say my body is at rest. But it could be, it is possible that the car was already moving and I start looking at it now. So, at instant 0, it will have a certain position also. You can talk about it like that. So, you see with this scientific notation, you have made an extension and a better way to describe where a particle is located at any instant. Notice, if I were to change this time, say instant 1, that means position at instant 1 second, position at instant 8 seconds, it could be any value, position at instant 15 seconds, likewise 22. So, this is a possibility of putting any values over there. So, 0 when you start looking at the motion, 1 second, 1 hour, 1 minute, whatever is your criterion to look at where the particle is located. Because if you are talking about an aircraft, you can't be only talking about seconds. You would say, okay, in so many minutes the aircraft took to this height. That means it travelled a certain distance along this line. And then in that case, there will be no point in saying, okay, after 60 seconds or saying after 360 seconds. It is better to put it in minutes, or it is better to put it in hours. So, those kind of possibilities are also there with this notation only. One more important thing that is there, and that is you can have x minus t, x minus 4. What would that mean? X minus 4 would mean that if this is x0, what was happening to the body before this time, 4 seconds before this time, x minus 4, that means time can never be negative, but it is only referring to a time which has passed. Like we talk about past, present, future, same way the time that you talk about is going to be time which you had considered earlier. So, if the object was stationary, it was stationary for an hour, and now when you start looking at it, you say, okay, it is now moving. So, all the x0 and positive values for time, it is moving, but what happened before that? It was stationary. So, you will say x minus 4, position was 0, x minus 25, position was 0, but x plus 4, it has moved to a new location. You can reverse this order as well. That means, if a car was moving and it comes to a stop. So, all the time, positive time after that is going to show that it is stationary. However, the time negative, that means time before you started looking at the motion, was all in different positions. So, position xt becomes a very important tool in a way to describe motion, in a way to describe the position of an object, and in a way to talk about at what time the body is located at what point. And therefore, if you recall the entire lesson, what have you learned today? You have learned that you can talk about rigid bodies, you can talk about rigid bodies as point objects, you will have to talk about rest and motion in terms of surrounding, in terms of time elapsed, and you will have proper definitions for when you say the body is at rest, for when you say the body is in motion. And then you say, okay, this surrounding will have a special scientific name and you call it the frame of reference. And this frame of reference, we have limited our study to saying that is stationary or is moving with a constant way, in a constant speed in a particular direction. But it is not going to be accelerating, it is not going to be vibrating, it is not going to be rotating, because that will make our study extension too much. Then you learnt a way to describe position of a particular particle at an instant of time, and your new notation that you have just learnt, xt, to say the position of the particle of the body at an instant of time. x0 therefore means the instant when you start looking at the motion. So, I hope you have learned the very basics of rest and motion, the very basics of kinematics before we go on to the next lesson.